Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out our playlist, watching our videos, liking, commenting, sharing those videos. Those are simple, free interactions that you can do that would help us grow and help us with the YouTube algorithm, so we would greatly appreciate it. Let's get into the current video. I want to take a look at the concept of connected topological spaces. Now, what do I mean by a connected topological space? Well, intuitively, so let's say this is within my my set X. Let's say I've got, maybe it's a subspace, but within this world here, I've got my topological space consists of this piece and this piece. So those two pieces there that look disjoint, we intuitively say, well, that's not connected. They're not together, right? Similarly, if I look at the real line and I were to take intervals here and here, and again, that's going to be, say, my topological space is the union of those two. Well, again, they're somehow disjoint, in other words, not connected. Well, how can we, because a lot of times we can't visualize topological spaces, especially give you, say, a finite set with some weird topology on it, or even just a real line with some weird topology, right? A lot of times we cannot visualize topological spaces. So therefore, of course, we have to have a formal definition of it. Well, let's start by looking at the definition of what is called a separation. So in a topological space x tau, what's called a separation of X is a pair of non-empty open sets U and V for which X is the union of U and V. So a separation is a disjoint union of non-empty sets that generates the whole space, or generates the whole underlying set of the space. Okay? Well, if there's no separation, we say that X is connected. Okay. So a connected topological space is one in which there is no separation of the set X. And notice that the notion of connectedness is written in terms of the topology of the space, meaning it is a topological property. If I have two spaces that are homeomorphic to each other, then if one is connected, then the other one is connected. If one is not connected, then the other one is not connected as well. Okay? Well, let's take a look at a specific example. And let me go ahead and pause it so I can write this up here. So here's my set X 1 through 5, integers 1 through 5. My topology is listed here. Then let's see if this topological space has some sort of a separation. Well, remember that if I look back at the definition, a separation is a disjoint union of open sets. In other words, can I come up with two open sets here that are disjoint and whose union is all of X? Well, let's take a look. I could have, well, 1, 2, and then 3, 4, 5. So X is equal to 1, 2, union 3, 4, and 5. Therefore, the set X is actually not connected because there is a separation. So therefore, then X equals this is a separation. Let's look at two other examples. Okay, so let's use the real line R, and let's pick the topology consisting of the usual topology on the real line. Okay, well, let's just get a visual again for the underlying set X is, of course, the entire real line. Now, what I want to do is let's see, is there a way that we could come up with a separation of this? Well, what that means is I would have to come up with a pair of disjoint open sets whose union is the entire real line. Well, let's just say this is 0 right here in the middle, and let's say one open set U is minus infinity up to 0, and then my other set V would have to consist of everything else, because the union of these two would have to be the entire real line. If I was to say, let's just kind of pick a couple of things. If I said 0 to infinity, not including 0, then of course those are two open sets, but their union is everything except for 0. Therefore, what I have to do is maybe pick something that would overlap. So let's say I was to pick something like -1, but then those two intervals would be not disjoint. They would overlap, so that doesn't work. You could say, all right, well, let's get rid of that. Let's go back to just 0, so that way the sets are disjoint. And then if I want to be able to take the union, so I get the entire real line, I would say maybe include 0. But then once I do that, then that's a closed set. But remember, we need disjoint open sets. So there's no separation, hence the space is connected. Okay. Now, this was just sort of an informal discussion that is in no way a proof that the real line with the usual topology is connected, but it just kind of gives you an indication of why it is. Okay. Second example, let's take the real line, and this time let's say the topology is the discrete topology. Okay. So R with the real line, tau is the discrete topology. And again, notice in these sketches, I'm not giving any sort of indication for the open sets. I'm only giving an indication for the underlying set, which is the real line. Well, for the discrete topology, remember what the discrete topology was. That means the power set is the same thing as tau. In other words, every single subset of the real line is open. So let's say U consists of minus infinity to 0. This interval is a subset of the real line, therefore is open. And V, well, again, it has to be disjoint from U, and the union has to be all of R. Well, let's go 0 to infinity. Now remember, over here in the usual topology, this was not an open set, whereas this one, of course, was. Over on the other side, though, for this example, in the usual topology, in the discrete topology, everything is open. So therefore, this is open, and this is open as well. And X, which of course in this case is R, is the disjoint union of U and V, hence is not connected. Okay. So connectedness is not just the set R. If I look at the real line and I give you just the picture of the real line, you're going to say, well, of course it's connected. But connectedness is also deals with the topology itself. So how exactly I'm describing the open and closed sets is what tells me whether or not a space is connected. So I mentioned that connectedness is a topological property, meaning if this space is connected and this space is homeomorphic to this space, then this space must be connected as well. Well, one of the building blocks for proving that is just showing that connectedness is preserved under continuous mappings. Let's take a look at the proof of that. Proposition. If f, which takes x to y, is a continuous surjection between topological spaces, and x is connected then y is connected. So the continuous image of connected is connected. Let's prove that. Okay. And the method for proof in this example is going to be proof by contradiction. In other words, suppose y is given by u union v is a separation. Meaning that u and v are both open sets and they're disjoint and their union is all of y. Well, suppose that that is a separation. Then since f is a surjection, the preimage of y is all of x. Okay, so the image of x is all of y, the preimage of y is all of x, and the preimage of y is, of course, the preimage of u union v, because y is equal to u union v. And since u and v are disjoint, this would be the preimage of u union the preimage of v. This gives me, again, remember that the preimage of y, though, is all of x. So let's squeeze that in there as well. X is the preimage of y. Y being the separation of u and v is the union of those two. Since this is a disjoint union, the preimage of the union is the union of the preimages. And since f is a continuous function, the preimage of an open set is open, so therefore this is open, and this, of course, is open, which means that the union is open. And now what do I have? This is not only an open set, but it's non-empty. This is an open set and it's non-empty, and they're disjoint. Therefore, what we have just done is we've created a separation of x, which says that the preimage of u, the preimage of v, give a separation of x. But of course, that's a contradiction, because we said that the set x was connected, which means it has no separation. Therefore, the assumption that we made that y had a separation is false, and therefore y is connected. Okay, proving the statement of the theorem. There's one more property that I want to show you for connected spaces. Okay. So here's the other property, or here's the last property that I want to show you. So let's say note. Suppose that x is u union v is a separation of that space, then, well, we know in particular that u is open and u and v are disjoint, and u union v is all of x. Okay? Well, what do we know about the complement of u? Well, the complement of u means it's everything that's in x, but not an element of u. But that's v. And therefore, we know that the complement of u is also open. What about V? Well, you just interchanging U's and V's. We know that V complement would be the X minus V, which of course is U, and we know that that's open. Well, what does this show me? In particular, U is an open set. Its complement, which, remember that the complement of an open set is closed. Well, the complement is also open. So what this tells me is that the complement, which is equal to V, V is open and the complement is open, so therefore V and U are both open and closed sets. So the idea is a topological space is connected if and only if the empty set and the entire space X are the only sets which are open and closed. Okay, just quickly illustrate that. If X tau is a topological space and A is a subset of X, is non-empty, open, and closed, then, well, I know that X is going to be A union everything that's not an A. Right? That's what X, no matter what A is, if A is empty or the entire set, X or anything in between, X is always the union and a disjoint union of a set with its complement, no matter what A is. But in particular, we're saying A is both open and closed. Well, if A is open, then this is open, and if A is closed, then the complement is open, and therefore this right here is a separation. And again, that just illustrates in sort of a vague way the fact that a topological space is connected if and only if the only open sets are the empty set and the entire space X itself. Thank you for watching, and please consider subscribing.